Let's solve 2023 first problem of USAJMO, USA Junior Mathematical Olympiad. After this problem, I will write a homework for you similar to this and useful for factorizing a term. Okay, let's start. There's many factorizing, famous factorizing that is important to work on, especially when x, y, z are integers. If you want to learn them, you can send message to my WhatsApp number in the description and comments. Okay, let's start. Find all triples of positive integers x, y, z that satisfy the equation. 2 times x plus y plus z plus 2xyz whole squared equal to 2xy plus 2yz plus 2zx plus 1 whole squared plus 2023. We have sum of 4 terms whole squared, so first you should know this. I write it for 4 terms. Also, if you have 3 terms, 2 terms, n terms, the idea is same. You write it twice. A plus b plus c plus d, a plus b plus c plus d. Then you say, okay, a squared we have b squared, we have c squared, we have d squared. And then we have a, then we have 2ab, ac, 2ac, add, 2ad, plus 2bc, 2bd, plus 2cd. Okay, now let's focus on our main equation. I write it as 2 times the left hand side. If you use this, it will be first one squared x squared, next one squared y squared, next one squared z squared, plus this one squared. It will be 4x squared y squared z squared, plus 2 times, like here, 2 times xy, 2xy, let's focus on this part first. 2xy plus 2xz plus 2yz. We've considered this thing now. 2x times this, 2 times x times 2xyz will be 4x squared yz plus 4x y squared z plus 4x yz squared. Okay, equal to this one whole squared will be 4x squared y squared plus 4 each term squared, like here a squared, b squared, c squared, 4y squared z squared plus 4z squared x squared plus 1, now plus 2 times this. Let's consider these 3 terms first. 2 times 2xy times 2yz will be 8xy squared z, 8xy squared z. 2 times this, 8x squared yz. 2 times this, 8xyz squared. Then plus 2 times this 4xy. This times this, 2 times that, 4yz. 2 times 4xy, 4yz, 4zx. One term is left plus 2023. So let me minimize it. Okay, to have more space. It's okay. Plus 2023. Now let's cancel the common terms. So 2 times 2xy is 4xy, and here we have 4xy. 2 times 2xz, we have 4xz, here 4zx. 2 times 2yz, 4yz, 4yz. We've cancelled 2 times 4x squared yz, 8x squared yz. We cancel x squared yz with this. 2 times this is 8xy squared z, 8xy squared z. Here 8xyz squared, 8xyz squared. And then let's consider another common terms. Here we have 2x squared plus 2y squared plus 2z squared plus 2 times 8. 2 times 4, 8, 8x squared y squared z squared equal to 4x squared y squared plus 4y squared z squared plus 4z squared x squared and plus 1 plus 2023. So it will be plus 2024. Okay. Now in next term, as you can see, always we have 2x squared, 2y squared, 2z squared. Also, you can write it as 2x squared times 2y squared times 2z squared. I can write this one as 2x squared, 2y squared. So I use changing variable. Look, the solution is from here, okay? So I want to use A, B, C, D again. It's okay, because it's as a lemma, it was identity I wanted to explain for you. Because it's not good to use repeated variables. So I say I consider A equal to 2x squared, B equal to 2y squared, C equal to 2z squared. So if I write this one, it will be A, the next one B, the next one C, this one ABC, this one 2x squared, 2y squared, AB, this one plus BC, this one plus AC, plus 2024. Okay. Now here we can see that, for example, try to find at least one example for you. One way is to factorizing. You can say that, okay, if for example A is 1, then left side is BC plus B plus C. Right side is what? Is BC plus A plus B plus C. So if A is 1, this one equal to this one. Okay. So these fours are equal. Now we try to factorize. Okay, so I take all things to left hand side. So it will be A plus B plus C minus AB minus BC minus AC, something like Vietta's formula, plus ABC equal to 2024. So it is like Vietta's formula, for example, when we have x minus A, x minus B, x minus C. Then you say, okay, for example, it is x cubed plus, for example, x squared. It will be minus A minus B minus C. Then plus x, it will be AB plus AC plus BC. Then you say, in next term, it will be minus ABC. Okay, and it's similar to this. And if you consider 1 here, it will be what? 1 plus negative A, negative B, negative C, plus AB plus AC plus BC, minus ABC, if x is 1. And as you can see here, the signs are different, so we should multiply by 1. So I said if x is 1, this factorizing, it will be what? You can write a minus, I want to multiply by negative 1, a minus 1, b minus 1, c minus 1, equal to negative 1 plus a plus b plus c minus ab minus ac minus bc plus abc. Okay, so this term is what? This term is this. Okay, so it will be what? It will be this term. You take negative 1 to left hand side plus 1. So I've concluded that this term, let's consider, for example, it is t. T is what? A minus 1 times B minus 1 times C minus 1. If you take this here, plus 1. So if I write it, let me move this part. So you say, okay, it is T. So it is A minus 1 times B minus 1 times C minus 1. We take negative 1 to left hand side, it will be plus 1 equal to 2024. If we subtract 1 from both sides, it will be A minus 1, B minus 1, C minus 1 equal to 2023. Now, so let me erase this part. Okay, here the product is 2023. We should know prime factorization of 2023, which is 7 times 17 times 17. And now we know A was what? A was 2x squared. So each term is 2x squared. So it will be 2x squared minus 1. Next one is 2y squared minus 1 and 2z squared minus 1 equal to 7 times 17 times 17. So for one of them, I want to see which of them possible. For example, 2x squared minus 1. Can it be 1? Can it be 7? Let's write number of divisors here. The number of divisors is 7 times 17 squared. And we know it is at least x, y, z. The problem says are positive integers, I think. Yes, positive integers. So each of them is at least 1. At least 2 minus 1, 1. So we should only focus on positive divisors. And the number of positive divisors, you should add the powers plus 1 times each other. Because a divisor can be 7 to the 0, 7 to the 1, 2 cases. And 17 to the 0, 17 to the 1, 17 squared. 3. So we have 6 divisors. We should check all of them. 1, 7. Then the next one is 17. The next one is 7 times 17. The next one is 17 squared. 1, 2, 3, 4, 5. The last one is 7 times 17 squared. I've checked all cases. And the problem says about find all triples of positive integers. So let's consider these things. So when we consider 1, we will see, okay, 2x squared is 2. So let me write in another places. Let me erase this part. And let me analyze. I want to see which divisors are possible. So if I consider this part, okay, the first one, 2x squared, if you add 1 to both sides is 2. So if you divide by 2, x squared is 1. X is positive, so x is 1. This one is okay. The next one, 2x squared, if you add by 1 is 1 plus 7 is 8. So if you divide by 2, x squared is 4 because x is positive, x is plus minus 2 because x is positive, x is 2. The next one, 2x squared, if you add by 1 is 18. So if you divide by 2, x squared is 9. So x is plus minus 3, so x is 3. Now 7 times 17 is 7 times 7, 49. We have 4. 7 times 1, 7 plus 4, 11. Okay, so 2x squared is 120 if you add by 1. X squared is 60, so this case is not possible. The next one, 2x squared minus 1 is 17 squared. 17 squared is 289. 2x squared if you add by 1 is 290. And if you divide by 2, x squared is 145. Also here you could say, okay, this 17 squared plus 1. 17 squared plus 1 is not perfect square. Is not, because it is twice perfect square. Okay. So we've considered that, and it's not possible because 145 is not perfect square. The last one, 2x squared. You add 1. 7 times 17 squared is 2023. You say, okay, it's 2024. If you divide by 2, it's x squared. Is 1012. Okay, so you should check that is it perfect square or not. It's multiple of 4, so you say 4 times 2 times 4, 821. 5 times 4, 12, 3. 4 is perfect square, 253 is not perfect square, so it's not possible. So the only possible cases are, they can be, let me underline, 1, 7, 17. These three cases were possible. The other cases were not possible. So 1, 7, 17. If you want to check, each of these numbers can only be 1, 7, 17. Only these cases. So, because we have two 17s, of course, so two of them should be 17, and one of them should be 7. Okay, these cases. So, the other things are permutation of these things. So let's check for x, y, z. For first one, for example, x2x minus squared minus 1, we've calculated 18 over 2, 9, 3, 3, and this one 8 over 2, 4, and it will be 2. So the permutations are also 3, 2, 3. The problem is symmetric with respect to x, y, z. 2, 3, 3. Okay, so the whole solution is this part. We have these three answers. Let me write another factorization for you. Try to factorize these terms. One of them is as homework number 1, a cubed plus b cubed plus c cubed minus 3abc. Try to factorize this. Write it as product of two terms. The other one is a squared b plus ab squared plus a squared c plus ac squared plus b squared c plus bc squared and plus 2abc. Also try to factorize it. Try to write it as product of three terms as homework number 2. Okay. There are some other factorization it's good to work on. Vieta's formula helped us in this problem. Without that also we could factorize. So two important things you should know: Vieta's formula and Newton's sum. We can solve Stanford hard problems of Stanford Newton's sum with this idea, SMT Stanford Math Tournament. And useful these two formulas, and we have some other formulas that you should memorize in algebra, number theory, and we have around 40-50 important formulas in geometry, also important ideas in combinatorics. For example, when we have lines, circles, some points inside that, outside that, on left side, on right side. In recursive sequence, we have an important question that helps you to solve IMO problem. If you want to know them, as I said before, feel free to send message to my WhatsApp number in the description and comments. Please don't forget to subscribe, turn on the bell, and like the video. Thanks. Take care. Be safe. Problem number 2 of 2023 USAJMO proposed by Holden, geometry problem. Okay. Let's read it. In an acute triangle ABC, let M be the midpoint of BC. Let's draw. Okay, in this triangle, acute triangle ABC, M is midpoint of BC. Let P the foot of the perpendicular from C to AM. So let's draw AM. And let's draw a perpendicular. Let me draw exactly through A. Okay. And then the perpendicular from C to AM. Okay. The angle here is around this 90, 22. Okay. So 22, it is our perpendicular. So this point is P, and the foot from C to AM. Suppose that the circumcircle of triangle ABP. So we should draw circumcircle of triangle ABP, and if we draw, we should enlarge. Okay. This one a little larger. more. Okay. So it passes through BP. Also, it passes through A if we enlarge it a little more. Now, the rest. Okay. So we can say this circle now passes through ABP. So the rest says what? Suppose that from C to AM, suppose that the circumcircle of triangle ABP intersect BC at two distinct points B and Q. So this point is Q. Then it says let N be the midpoint of AQ. So let's draw AP here. AQ, midpoint of that. So we can consider the length is 152.76. Okay, it's around this point. And the midpoint is what? N midpoint of this. Okay. It is this. The problem says prove that NB equal NC. In some problems like this, we should work a little on assumption and a little on sentence. For example, the first thing that we know NB equal NC, you can draw this line, or you can say, okay, N should lie on perpendicular bisector. It is the definition of perpendicular bisector. So it is equivalent that N lies on perpendicular bisector of BC. And because M is midpoint, we have this, it's good. So it is equivalent that NM, y NM is perpendicular to BC. So we should prove it. Let's draw a line from N to M. We want to prove it is 90. So this part we want to prove is 90. We want to see can we find a cyclic quadrilateral. This 90 not related for creating a cyclic quadrilateral. But let's do something. It is midpoint, and if we find, for example, if this part was equal to something else, was good because we could use Thayer's theorem, means this one. Application of similar triangles. If it is parallel to this over this equal to this over this. For a special case, we call it Thayer's theorem. In a special case, if it is equal to this, we call it midpoints theorem. Okay. We see that we don't have anything like that, but because M is outside, we know MP MA equal MQ MB. The reason is what? In cyclic quadrilateral, we have 4 basic rules, and one of them is this. If you have P, for example, in general, A, B, C, D, you should memorize it, and the proof is by similar triangles. PA times PB equal to PC times PD. Okay. Now we can say what? We can say that if we apply this theorem here, MPMA equal MQMB. Okay. Let's write it. Okay. Let's write MP MQ MA this times this, like this part. You say, let me write it. PC times PD equal to PA times PB. So MP times MA equal to MQ times MB. Now, here, look, we see this 90, and we see MPMA. So we say if you have another cyclic quadrilateral, it's good, you can create this. And if we work on, as I said before, for example, in altitudes, if we draw altitudes, we have, let me tell you, 6 cyclic quadrilaterals. And the proofs are not hard. If you want to learn them, the properties of altitudes, angle, internal angle bisector, external, the formulas in those things, feel free to send a message to my WhatsApp number in the description and comments. Okay, so if I draw this altitude, and for example, let's call this one N. We have N, so let's call it K. As you can see, these two 90s see the same side, and it is a property that if we have a, for example, quadrilateral, that the angles that see the same side are equal. For example, it is A, it is B, it is C, it is D. A1 equal, it is the second property. We have two more properties. A1 equal to B1 is equivalent that ABCD if and only if ABCD is cyclic. So here, because two 90s see the same side, we can conclude APQC is cyclic. APKC is cyclic. And again, we do the same thing. We do this action here. MP times MA equal MK times MC. So MP times MA equal to MK times MC. And because MPMA, MPMA are common terms here, we conclude what? MQMB equal to MK MC. And because M is midpoint of BC, so we can cancel MBMC and we conclude MK. This equality was for MBMC. Now we can say MK equal to MQ. Okay, and that's important thing here. MQ equal to MK. Now we can use Thayer's theorem, or as a special case, midpoint theorem. That it was what if we drew this. If this over this equal this over this, then these two lines are parallel. Now Qn over Na is 1. Qm over Mk also is 1. So we conclude that Mn is parallel to Ak. We know AK is perpendicular to BC, so we conclude MN is also perpendicular to BC. And it was the thing that we wanted to prove, so this part we've proved. So this was okay, for some if we consider question mark, and this part is okay. So we've proved that NB equal NC. Let me write a homework for you related to exactly this property in combinatory, in geometry, that when we have cyclic quadrilateral as homework, try to solve BMO2, British Mathematical Olympiad, round 2, question number 1. I can say BMO and USAJMO are the most prestigious national exams in Math Olympiad, so try to, let me move it, okay, like this. So try to do this problem as homework. And as I said before, in combinatorics we have 4 important lines. Medians, for example, length of median, properties of medians, angle bisectors. For example, length of internal angle bisector, which is 2bc over b plus c cos a over 2. Length of AI, which I is in center, which is bc over s cos a over 2. For example, AIA, IA is x-center of A is BC over S minus A cos A over 2, and lots of formulas. And then after that, perpendicular bisectors. After that, altitudes. And then cyclic quadrilaterals. Except this, we have only some quadrilaterals. We have something like, for some Seebeck's theorem. They are short theorems, we can prove them quickly, but these things are so much important because in each problem we have some of them. For example, in previous problem of USAJMO, if you worked on altitudes, you know all 6 cyclic quadrilaterals, and we have lots of important formulas in altitudes. One of them, orthic triangle, we had problem in AME that orthic triangle was useful. The length of orthic triangles are A cos A, B cos B, C cos C. And for example, the angles are what? Angle tracing in each of them. Okay, if you want to learn those important formulas in geometry that are useful in all exams, up to IMO, from AMC, Feel free to send message to my WhatsApp number in the description and comments. Okay, let's solve the last problem of first day. Problem number 3. In each day we had 3 problems. Okay, in USAJMO, USA Mathematical Olympiad for juniors. So let's solve the problem. Let's read. Understand the problem first is what? Consider an n by n board of unit squares for some odd positive integer n. Okay, so it is important n is odd. We say that a collection C of identical dominoes. Dominoes means what? 2 by 1 and 1 by 2. Okay, this type. Horizontal and vertical. Is a maximal grid aligned configuration on the board if C consists of n squared minus 1 whole over 2, all over 2 dominoes, where each domino covers exactly 2 neighboring squares and the dominoes don't overlap. So look here, and it says C then covers all but one square on the board. We have n squared cells, the number of cells. It is odd because n is odd. So if we want to cover with dominoes, we should subtract 1. Now it will be even. And if we divide by 2, it will be number of dominoes. Okay, so let's consider, for example, 3 by 3. Let's consider a maximal grid align configuration. For example, this one, this, and this. Okay, this cell is left. And if we replace n with 3, it will be 9 minus 1, 8 cells. We should cover over 2. We have 4 dominoes. Okay, then it says we are allowed to slide but not rotate a domino on the board to cover the uncovered square, resulting in a new maximal grid aligned configuration with another square uncovered. Okay, so let's slide one of them. For example, we can slide this one or this one. If we slide this one, then it will be this. I should remove this one and finish. Okay, for example, this one is now, it says, with another square uncovered like this. Let K of C be the number of distinct maximal grid aligned configurations obtainable from C by repeatedly sliding dominoes. So in this part, if I consider, let me tell you, if I slide this one, then for example, I move it here, then I remove this one. Now the uncovered cell is this. Again, I can do the same thing. That's the reason it says repeatedly. Can do it again. This. Okay. So then the problem says what? Find the maximum value of k of c as a function of n. Okay. So let's see how can we solve this problem. Look, in this exam, 2 of the problems can be solved with this idea. And in IMO, we have lots of problems. In BMO for British, IMO International, USAJMO, that is not for only juniors. You should consider in problems like this. This idea especially can solve so much hard problems. You can use a small example, okay? One approach is this, and so much important approach. Considering a small example. If you want to learn other approaches that are so much useful and how to apply them. For example, in recursive sequence, we have an important question you should ask always, and with that question, it helps you to solve all recursive sequence problems, 90% at least. And also IMO problems we can solve that can be solved with recursive sequence. Okay, here N1 is only one cell. We can't reach any important thing. Let's start with, let me tell you, also if you consider this one, we have only one. It can reach only to itself if n is 1. The problem says n greater than or equal to 3. No. Okay, for n1 we have 1. The answer is 1. Let's check n3. Okay. And now we want to consider all cases. Look, if you consider another important thing, coloring. If you color a 3 by 3, we want to see which cell can be uncovered. We have, it is black, it is black, it is black, it is black, it is black. We have 5 blacks, 1 white. And because each domino always select 1 black, look, if you select here or here, always select 1 black, 1 white. So the cell that is left should be black, okay? Because we have 5 blacks, number of blacks, 5, number of whites will be 4. So By 4 dominoes, we cover 4 whites, 4 blacks, so 1 black will be left. So we have how many cases? 5 cases. And now I want to consider all cases here. Let's consider first this part. For example, it is empty. And because it is empty, we can consider, okay, all others are also similar to this. Now, when it is empty, what are the cases that we can do? We should cover it is empty. Okay, so let's analyze this one. So this cell can be covered like this, or let's consider one of them and see we can reach to what cases. Okay, for example, consider this one. And then we can reach, if we slide this one, we can reach this one. I'm sorry, this. And if we slide this one, it goes here, 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 here. And then we can slide this one. It goes to this port, this port, this port, this port. So from this case, we have 4 cases. So the answer for this one is at least 4 if n is 3. Now we want to see, do we have more? So if we consider other cases, let me write, okay, I want to consider what about other cases. If this one is empty, this one is not covered, so this one is covered by this one or this one without loss of generality. Suppose this one, then this one has to be covered, this one, this one, this one. Then in this case, we can't reach to any other cases. So we have only one 3 by 3. So still the corners are better. Now for corners, let's see, can we have any other case that is better than this? So if, for example, this one is empty without loss of generality, is not covered. So here I consider, for example, these two things are, for example, pointing to this. So we know, for example, suppose in this case we consider this one like this, again this one like this, but here we consider horizontal, let's consider vertical. And as you can see, it is symmetric again. Look, we have 3 times like this, 3 like this. Okay, so here again for this case we can reach 4 cases. Now let's consider another one. Let me consider next one with green. Now in next case, suppose for example we don't have these two because we've considered, suppose for example it is covered like this, then it is covered like this, it is covered like this, like this. Okay. And now let's see, if we consider it is exactly similar to this one. Okay, look, these two are similar to this, and this one is similar to this one is similar to this. Okay, and also with starting this case, we can reach 4 other cases like this, because when you reach from some case to other case, you can, it is, we can say it is bilateral. If you reach from A to B, you can reach from B to A also. Okay, so we've proved here all, the answer is at most 4 again. So for N2, we found that the answer is 4. Okay, for N1, we've reached 1. For N3, we've reached 4. Now, let's see for N5, for example, we can find what examples. Okay, for N5. Okay, so here I consider for 5 by 5. This one is empty again. And then we have these. Then we say, okay, after we move these, let's consider this one. Then this one will be empty. This one, this one, this one, this one. And this one. And then here it has to be like this. But when this one is empty, we want to have this. Then this one is empty. It seems that we can't do anything. Okay. So let's see, this empty can go to what places. When we move this one will be empty. We move this, we move this, we move this, we move this one, this one, this one, then this is empty. So we move this one and finished. Okay, so we have one case in the beginning and we can create 1, 2, 3, 4, 5, 6, 7, 8 more. So it is 9. So the answer here is at least 9, but we've not checked all cases. And let's see, for 1 it was 1, for 3 it was 4. So look, for 1 it was 1, for 3 it was 4, for 5 if not proved it is at most 9, but we guess our claim. We want to check. If it is 9, let's check. For 7 we guess it is what? It is 1 squared, 2 squared, 3 squared. So for 7 we guess it is 4 squared. Okay. So let's check first for 7 that is it 16 or not. Okay, for 7 by 7, n is 7. Now let's consider for 7 by 7 the same thing. If we consider this one, this one, this one, this one, this one, this one, like spiral, this one, then this one will be empty, this one will be empty, this one, then this one will be empty, this one will be empty, this one will be empty. We can't do anything. Okay, let's fill the rest. And look, let me tell you, in this problem, we should work on two parts. Greater than equal what, less than equal what. We should prove one part with example like other problem of this year. When you want to find something maximum or minimum, you should do the same thing. For example, for 5, when we find 9, the answer is at least 9. So this part is with example, and this part is with proof. Okay? And we should reach same number for both sides. So in this case, we say, okay, it goes here, 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 by sliding repeatedly. Here, 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 this one, this one, this one, this one, this one, this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So one case in the beginning and 15 case, it will be 16. So again here, we proved it is 16. So in these two parts, we proved that the answer is at least 9. The answer is at least 4 squared. Okay. Now we want to prove same thing, one part of the problem. So what's the relationship here? For 1, 1 squared, 2 squared. For general and n is odd. It is what? As you can see, we want to prove it is 7 plus 1 over 2. N plus 1 over 2 whole squared. We want to prove it. Okay? We want to find an example like this. So let me draw. Okay, suppose it is odd number n by n. For example, it is 1, it is n, it is 1, it is n. So if we want to find example for general n, so we consider it is this. Because n is odd, we know at the end one cell is left, we have even number of cells are left in this row, so at the end we will have this, okay? And so on. Then we have this one, because again, this cell is covered by the row. So in this column, even number of cells are left, so it will be like this again. And let me show you. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm sorry, it's 12. So let me draw a figure that is 13, for example, by 13, odd by odd. Okay, because it was 12 by 12, it's better to show something that has odd number of cells in each row. Okay, let's minimize it. It has 15 cells in the rows and columns. Okay, so now in this case, suppose this cell is empty, so it will be like this, because even numbers are left here. You continue like this and you say, okay, dot, 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 it will be this. Now here, odd number of cells, we have odd number of cells in this column, but because we ignore this one, even number of cells are left. So if we continue like this, or something, this, it will be covered by this part. Again, similarly, we write like this, and so on up to this part, then this part, this part, this part, this part, and let me tell you, it goes, for example, because here, because one cell here are left, so odd number of cells we have, so it goes up to this part, dot, 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 So in next level, we have these, because we have even number of cells are left in this row, because one cell is removed, it goes up to this part, dot, dot, dot. And then in next step here, we have 1, 2, 3 are left, 3 cells are removed, so n minus 3 will be even, so it goes up to this part. Again here 3 are removed, so it goes up to the last part. Again here 3 are removed, 4 are removed, 1, 2, 3, 4. So it goes up to this part. Okay. Now look, let's consider this part. We say what? One cell is left here, so the other highway will like this. Now I want to use induction. And how I want to use induction? Because n is odd, I want to use for some n minus 2 or n minus 4. I want to use this figure, okay? I want to use n minus 4 to n, okay? And if I consider, I know I slide this one up to this part, this one, and then it will be like this to right, this to bottom. And when I move this, the next one will be this. And look here, the next empty after sliding all of them, the next empty will be here. And again, if I cover this red part, it is n minus 4, n minus 4, which it is odd because n is odd. So we can use induction. We wanted to prove what our claim was. It is answer is at least n plus 1 over 2 whole squared. And for n1, for example, n3, n5, and 7, we proved here. Okay, and because we want to use n minus 4, we can say, okay, in the base cases, you can only also select, for example, 1 and 3 as base case. It's enough now. In this case, only these two parts are enough. You say in this red, so one case, let's see, answer is at least 4. One case for the beginning, let's see how many sliding do we have outside the red box. So 1, 2, how many dominoes are here? N minus 1 over 2, because we have n minus 1 cells here in this board. So we have n minus 1 over 2 dominoes. We can move them. Again, this board also, it will be n minus 2. For this board also, it will be n minus 2. And then for this board, as you can see, it is n minus 3 over 2, because n minus 3 cells. Plus, now here I want to use induction. So when I move these, I don't count it here because I count it in the first position of the red box. So for n minus 4, if I replace n minus 4 here, it will be n minus 3 over 2 whole squared. Let's calculate it. It will be, if we use common denominator 2 here, n. We have 4n. Minus 1, minus 1, minus 1, minus 3, minus 3, minus 6. Plus 2, plus n minus 3 whole squared, which is n squared minus 6n plus 9, all over 4. So this part is what? Negative 6 plus 2, negative 4. If we use common denominator 4, it will be 8n minus 8 plus n squared minus 6n plus 9. So it will be what? It will be 8n, n squared first, 8n minus 6n is plus 2n, 9 minus 8 is plus 1, all over 4. So it will be n plus 1 whole squared over 4, and it will be n plus 1 over 2 whole squared. Okay? So we proved that the answer is greater than equal to this. Now the next part that we want to prove is why the answer is at most. Let me tell you, n plus 1 over 2 squared. Okay. Let me copy it and paste the table again. Let's use this table again. Control C. Control. At first, I want to focus that the holes can be in what places, okay? So here, we said the holes can be only, for example, in black cells. Set. Now, if I have, for example, let's focus on the cells that can be hole. I consider them 1. Okay, if it is 1, if it wants to go to the other one, it goes to this one or this one. Okay, let's consider these holes. Let's consider first only the outer layer of this. See, the holes can be in what points? So you say 1, 1, 1. And also you write it as 1, 1, 1 here, 1. Then this cell, sorry. When we have a cell here, when you move it here, this cell will be empty. 1, 1, this alternatively. Unlike this part. If we are in outer layer, if only sliding our inside outer layer, we can reach these ones, okay? Now, suppose that, for example, we want to, instead of, for example, sliding a domino here, we want to slide something like this, okay? Then we can say what? This one goes here. Okay, so we can't have one in this layer, okay? So this layer will be blocked, okay? So here the other ones can be here or this one here, 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 on this layer. These four for these ones. And now again, this layer is not possible to have ones. If we move this to this part, we can have in this layer. Okay? So here it is 1, again it is 1, 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 1, 1, 1 here, 1 here, 1 here, then in next step, we can't have in this layer. Okay, if we move, for example, this to this one will be here, 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 and finished. Okay, let me erase this red part. So this layer, we have how many layers? The first layer, if you remove it, 2 will be left from columns, 2 will be removed from, two rows will be removed, 2 columns will be removed. So you have 1, 2, 3, and at the end, how many layers are there? The first one, second one, third one, to n plus 1 over 2. Because we should consider also this layer, but after this, I consider that in which cells we have 1 or 2. The next case, we consider green cells. Okay, for example, we consider it is 2. It is 2. If we have this, if we want to move, these 2's can be reachable from each other. So these 2's, these 2, 2. If we draw all 2's here, you will see 1 and 2 are not related to each other, okay, as empty cells. 2, 2, again. We can't have this layer because this layer is for ones, and we can have inside that 2 here, 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 here. As this part, 2, 2, 2, 2, 2. And this part, 2, 2, 2, 2, 2, 2, 2, and last part is this. Okay. Now we want to count the number of ones and number of twos, okay? So let's see, let me explain for you. At first, we want to see the layer, the maximum layer that is n. How many ones are there? You say here, how many ones are there? 1, 1, 1, 1, n plus 1 over 2, okay? Because there are n cells, in first one, in third one, in fifth one, up to nth one. n minus 2, 1, we have this. So if we consider the numbers 1, 3 to n, it will be n minus 1 over 2, because it is arithmetic sequence with common difference 2, plus 1. It will be n plus 1 over 2. And on each side we have n plus 1 over 2, but we've counted the corners twice, so we should subtract by 4. So if we factor from 4, it will be n plus 1 over 2 minus 1. So it will be what? 4 times this number. It will be 4 times n minus 1 over 2. Why? Because it's n plus 1 minus 2, n minus 1 over 2. It will be 2 times n minus 1. So in the highest level, it's this. Here, I want to prove the number of white cells, the number of ones equal to n plus 1 over 2 whole squared. Again, I can use induction. In this part, I found that it is 2n minus 1. Then let me tell you, inside that. Inside that, it will be this figure. If I use same formula, it is for n minus 4. n minus 4 plus 1 over 2 whole squared. So it will be what? It will be 2 times n minus 1 plus n minus 3 over 2 squared. So we consider 2 times n minus 1, or let's write 2n minus 2 plus n minus 3 whole squared. It will be n squared minus 6n plus 9 over 4. And then it will be 4. It will be n squared minus 6n plus 4 times 2n, 8n. 8n minus 6n will be 2n. Minus 4 times 2, 8 minus 8 plus 9 is 1. So it will be n plus 1 squared over 4. Or n plus 1 over 2 whole squared. It was the number of ones, okay, that we've calculated with, let me tell you, with induction. Now, if you want to calculate the number of green 2s, we have one layer. For this one, it is for n minus 2. Because it starts for n in n minus 2, let me draw the circle. It is for n minus 2 if I consider from this part to this part. So number of 2s by the same way, because we proved for n it is n plus 1, n plus 1 over 2 whole squared. For 2s, it will be n plus, because it's n for n minus 2, it will be n minus 1 over 2 whole squared, number of 2s. So we will see number of reds are greater, and it is n plus 1 over 2 whole squared. But we proved what? We proved number of empty cells that we can create is at most n plus 1 over 2 whole squared. We've not proved that number of configurations is at most n plus 1 over 2 whole squared. But if I prove for each hole, for example, for this red, this one, if for this one only we can have one configuration, if we start from a specific configuration, then we can say the problem will be solved. So now our goal is this. For example, we have a hole here. We want to see only in one way we can reach this. Only one configuration is reachable, and the hole is exactly in this point. Then the problem will be solved. So let's prove this. I want to prove this part by contradiction. Okay, so suppose that if we color with black and white, we said, okay, the hole should be from black. It's not important. It's here, for any hole. I want to say it cannot be, we have only one configuration with that hole. So let's prove by one configuration with that hole. Let's prove by contradiction that, for example, suppose for one hole here, 1, 2, 3, 4, for example, this hole, because the color should be black. Okay, we said in the beginning of the video, because we have one more black. Each domino covers on exactly one black and one white, so the cell that is removed should be black. Suppose the hole always should be black. Consider this one. Now, suppose the first one is C, and we can reach two cases. Okay, so let's minimize this. Let me remove this part, because I want more of that figure. Okay, for example, we have this one, and I think we draw smaller grid, it's better. So let me draw another grid. So here, for example, suppose this we have this hole, okay? Now, suppose we have C. Suppose we've reached to two cases, for example, case A and case B, and in both of them have same hole, okay? And they are different. So suppose, for example, this one is, let's consider this one. Control Z, Control Z, Control Z. Let's copy again this part, okay? Suppose it is, for example, A, it is B, and these are different, the whole are same, and they reach from first configuration C. Because we said it is bilateral, means if you reach from C to A, you can reach from A to C, and also if you reach from C to B, you can reach from B to C. So we can say that we can reach from A to B, okay, by sliding the dominoes repeatedly. Now suppose that, for example, here when we want to go from A to next step, without loss of geometry, suppose we have this one and we, for example, move this domino to right. So let me minimize the figures. Okay, now let's copy from this part. Okay, when we slide this one, it goes here. Let's remove this. Okay, so it is the first step after A. So let's remove this. For example, it is C, it is D, configuration D. And look, it is here. And suppose the first time, if maybe you say, okay, I want to say before B it was here, and we moved it, for example, to some other parts and to reach B. I say that suppose the first time that we see this hole is B. Okay, if it is not B, consider another one. So for this hole, we want to consider two cases that their distance is minimum. Okay, so we can say with our loss of generality, B is the first time that this hole again is empty by moving from this. Okay, now let's analyze the case before B. We know that if we move this because we want to have empty here, if we move here, we cannot move it to this position. Why? Because when we have this one empty, for example, we said it is black, if we color black and white, the other cells that can be empty are these. For example, if you want to move this here, then this cell will be empty, but this cell is white. So the only possible case is to move it to left. Right is not possible. So because here it is the first case that this one is empty, so you should mention it in the beginning of this proof. You should say, okay, I consider A and B with this hole. So look, I consider A and B with same hole that can be reachable from C, and their distance is minimum. We want to reach from one to each other. And look, we consider the distance is minimum between all cases that we have, for example, common holes. You will see at the end it will be useful, and their distance is minimum. Now here we say, okay, we had this and we've considered this to left side. Okay, so it is this, and as you can see, for A and B, because we've considered this part in A, this part in B are same. Now here, because we've moved this to left, it means that here the empty was what? Empty was here. And in B, because, let me erase this direction. Okay. In D, let's see, you move it here. Now the empty in D is what? Is here. And if you see, and for example, this configuration, we called it E. As you can see, in D and E, we have same hole again. But their distance is 2 less than A and B. Distance of D and E is distance of A and B minus 2. But we said we consider two cases that have same hole and their distance is minimum. The minimum number of steps that you can reach, for example, from A to B should be minimum. But distance of D and E is less than that. So we conclude that D and E should be same. They should be same table. Otherwise, if D is not exactly equal to E, it's contradiction because we found distance less than that because the distance of D and E is less than distance of A and B. But this one was minimum, so we can't find a distance less than minimum. So, and we said here A and B with the same hole, A is not equal to B. Okay, so because we know when A and B are not equal, these two things means the configurations are not same. We consider the minimum distance. If D is not equal to E, we reach contradiction. So we conclude D equal to E. When D equal to E means what? The next step after A and the previous step before B are same. Means distance of A and B is what? One step, two step is 2. So now let's analyze. It means what? It means that we have A, then D, then B. So let's draw these three configurations only. Control C here, Control V. Let's copy B again. Okay, we can only also copy by this. Control C, Control V, this part. Control V again, this part. Okay. Now let me erase this part. Let me erase this part. Let me erase this part with me. Or let's consider something. Let's erase only this. Let's erase only this. So it is B. It is D and E are equal. Okay, so we say what? We moved this to right. So it was this. So now it means we move this one to left. It is this. So as you can see, the difference in A and B is what? You move this to right, again you move it to left. So all other dominoes are same in A and B. So we conclude A equal to B, but it's a contradiction because we've considered that A and B are different. Okay. So we've proved this problem by considering a small example first. That was the key point. It helps us to find the answer, and then we try to focus on proving that. So let me write some problems as homework that you can solve with considering small examples. As homework number 1, you can solve this IMO problem. As homework number 2, it is this problem you can try. And as homework number 4, BMO2 2023 last year, question number 3. I also released all solutions of BMO round 2. You can find it in my channel in BMO section. And you can solve these two problems and you can check your answers by watching the video. And okay, if you had question or wanted to solve more problems with this idea, want to learn more approaches, how to start a problem from basic level up to IMO, general ideas in combinatorics, for example, in graph hangout from a vertex is so much useful, and some other things. If you want to learn them, as I said before, feel free to send message to my WhatsApp number in the description. 2023 USAJMO question number 4. It's a combinatorics problem. Let's try this, and we want to work on the ideas that here is useful. It says 2 players, B and R, play the following game on an infinite grid of unit squares, all initially colored white. Players take turns starting with B. On B's turn, B selects one white unit square and colors it blue. Okay, it is like this, and for example, because it says infinite grid, we can consider this. Okay, for example, B select this one, and it is B. Then it says on R's turn, R select 2 white unit squares and colors them red. For example, R select this one and this one. The player alternates until B decides to end the game. At this point, B gets a score given by the number of unit squares in the largest in terms of area. Simple polygon containing only, this part is important, blue unit squares. What is the largest square B can guarantee? A simple polygon is a polygon not necessarily convex that doesn't intersect itself and has no holes. Okay, let's consider here, we consider the answer. When you want to find largest or smallest, something like this, you should consider this. Answer between two intervals. And always one side is, for reaching one side, you should use example. For one side, you should use proof. For this problem, pause the video and try to see for which part we should find example, for which part it is proof. This part is example, because if you find an example, for example, B can always reach, for example, 1. Always we have this. Okay, so this one is always greater than equal 1, because it is 1 or greater, because the problem wants largest. And this one is with proof. We should work a little on example, a little on proof. Okay, let's consider here. I select B first. We want to find an example, see at least how many B's can we place. This B has how many adjacent cells? 4. So, the problem is how many B can you create that the B's are connected? Connected means, for example, let me tell you, it's B, B, for example, B, B. So, this is good because we can consider this polygon. Okay, we want to see how many B's can we place at most. So, when we place one B, it has 4 adjacents. R can remove 2 of them, and without loss of generality, we can say this one is empty because this one is symmetric. So R can remove 2 of them, 2 of them will be left. So we select this. Now how many adjacents are there? 6. After B places the second B, we have 6 places, 6 adjacent cells, and R can remove 2 times 2, 4 of them. So 2 will be left again. The 2 that will be left, one of these 2 things, they are symmetric, and these 4 things are symmetric. So we should consider 2 cases. That this one is left, or this one of these 4 cells. Okay, let's consider these 2 cases. Okay, in this case, we have, for example, B here. In this case, we have this shape. Now, in this case, how many adjacent are there? 3, 8. And R can remove 6 of them. Then we can place one more B. Okay, so in this case, we can place one more B here or here or here by symmetry, 3 places. So 4 is reachable here. Now in this case, you say, okay, the adjacents are 1, 2, 3, 4, 5, 6, 7. Yes, 7. 1, 2, 3, 4, 5, 6, 7. Now I can remove 3 times 2 because after 3B R also plays 3 times. 3 times 2 because in each turn R places 2 R's. So 6 of them will be removed and 1 will be left. So because 1 will be left here, 4 is reachable also. Okay, and let's check all cases. It can be here by symmetric. This one is similar to this one. This one, it will be this is similar to this one. And this one, which is also similar to this one. So we should consider 4 cases. Here we should consider 3 cases. Let's consider these cases to see can we reach 5 or not always. Okay, let's consider these 3 cases. One of them here, the other one this position, the other one. Let's focus on case 1 first, and then we focus on case 2. So we've considered this case, and now let's consider this case. Okay, so In this case, we have how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And after 4b, then R plays 4 times. 4 times to 8, so we have 2 places at the left. 5 here is reachable. If we consider this one, 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces are good. And then 4 times, let's consider 2, 4, 6, 8, 9, 9 spaces. And then after 4 turns, R plays 2 times, 4 times to 8. One of them will be left. Okay, so 2, 2, 2, 2. Because one of them will be left, so 5 will be reachable also here. This one, 1, 2, 3, 4, 5, 6, 7, 8. Oh, this one. Because R plays 4 times, 5 is not reachable. Okay, and because in one case 5 is not reachable, and let me tell you something. Here, we said how many places we have here? 3, 3, 6, 10, and 6, 8. So R removes 6 of them, 2 will be left. But this one is related to this case, and this case is bad. Okay, if all of them were, in all of them 5 was reachable, then we could understand that, okay, the answer is at least 5. But it is not necessary our answer. We can say up to here, we proved answer is at least 4, but maybe answer also is greater than 4. We should work a little on proof. See, for example, R can play in a such way, for example, to block B to such that B can only reach 4 at most. Let's check also second case, because it's good that we see we can reach to which cases. Okay, let's consider this case. Let me draw the fourth B by another color, by black. Okay, so 1B can be here, adjacent to, we said, let's consider, 3 B's are like this. Okay, it's also similar, but let's draw the same pattern. Okay, so this one is B, and one case is we have B here. Another case is we have B here. Another case is we have B here. Another case, so 1, 2, 3, 5. B here is another case. If B is here, it's similar to this one. If B is here, similar to this one. Let's check if B is here. It's similar to this one. Okay. And we've considered 4, we should consider 4 cases. And here also we said all other cases are similar to one of them. Now, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 5 is reachable because R can remove 4 times to 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. 5 is not reachable. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 5 is not reachable, and also this case we've checked in previous case 1, 2, 3, 4, 5, 6, 7, 8. Again, 5 is not reachable. Okay, so up to here we proved that the answer is at least 4. Now we want to prove, and look, one of the figures have a good form, this one, a 2 by 2 that is not reachable. So if we focus on this, and look, R's surrounded these 4 B's. If we do the same thing, means we focus on 2 by 2's. So let's consider the grid and divide it, split into 2 by 2's. Okay, we consider this grid and I want to divide it to 2 by 2's like this. Okay, and then we want to focus, look, in previous part we said, okay, B can do this part, this part, this part. Now here we want to focus on R, that R can play in such a way that, for example, limit B, and C, R can do something to limit B to at most how many cells. Look here, when we draw this, we want to surround B. We say, okay, if B selects something here, then R select 2 adjacent to this B. And how? R select in the 2 by 2 that B belongs to, R select, and it is a unique way, R selected these two things. For example, if B selects here, then R select these two things. And let me tell you, if B selects here, we don't have any option. So, for example, we can consider 2 R's in another places. Any places you want. Okay, R here. Any places you want. If 1 or 2 of the possible moves for R are not possible, you can take any two white squares and select them and change them to red. Or once if one of them is not possible, you can select one other cell and change it to red. Okay. And for example, look, if B select, let me tell you the reason is what. If B selects here, then we select RR. If B selects here, then we have RR here. If B selects here, then we have RR here, and it will be blocked. And we guess the answer is at most 4, but we should prove it. Okay, how? By this strategy. So, let me prove how we can say, I say that, suppose that, let me consider, for example, suppose that we have a figure that contains B. Okay, now suppose we have a figure that, for example, any figure, like this, for example, our polygon, something like this, that contains B. And from each B to other B, you can find a path to reach this. Okay, so we say, suppose, for example, without loss of generality, 1B is here. We can reach to other B's. Because 1B is here, we know the time that we B placed this one are blocked with this way. So the next B that is adjacent to this is here or here without loss of generality. Suppose this is. Again, this B doesn't have any paths to these parts. The only adjacent thing to this B or this B, one of them, because if they are connected to others, if the answer, we prove the answer is at least 4. Okay. Suppose answer is, so we want to prove that why it is at most 4. If it is greater than 4, we know it's greater than 2. So we have 1B or 1B here because they should be adjacent to one of them. And because of this, we know it is blocked because of these 2 R's. Then these 3B should have, for example, like this. One of them should be adjacent to one other B's because from each B to each set, for example, here they are connected. You can go to other B's. So the only cell that is left is this one. And we know when we place this here or place this here. So these 4 B's blocked. So if we consider each B, we have at most 4 B adjacent to each other. We can't have more than 4 B. So we proved that the answer is at most 4. Okay, so we've analyzed at first a small example, started with B, 1B, 2B, 3B, and the shapes helps us to understand that 2 by 2 helps in previous part. 2 by 2 works and in this part. And then we focused on dividing split into 2 by 2 grid. Into 2 by 2, the grid split the grid into 2 by 2s, and we've proved. Let me tell you a similar homework. We call this one grouping, a homework of IMO related to this problem. Okay, this 2018 IMO problem is, you can do it as homework. It is similar. The idea is similar. You should consider groups, split the figure into different groups and solve the problem. Okay. If you want to solve similar problems related to groups, find the answer minimum greater than what, less than what. And here also look, find the greatest one. If you want to learn the ideas when you want to find something minimum, maximum, and solve different cases of those types of problem, as I said before, feel free to send message to my WhatsApp number in the description and comments. In this video, we want to solve problem that is in common with USAJMO and USJMO. It's for junior. It's question problem number 4 of USAJMO, United States of America, Mathematics Olympiad, and question number 5 of USAJMO. USAJMO, which is for juniors, and 2023. The problem is the combinatorics problem, and in this problem I want to tell you so much famous idea, and I will leave some homework at the end of the solution. The idea, I can say, one of the most useful idea, especially in combinatorics, also in other topics can be useful. So let's start. It says a positive integer a is selected. Okay, so a belongs to positive integer. This sign means belongs. And some positive integers are written on a blackboard. Okay. So for example, we have x1, x2 to xn, or because we have n here, xm on blackboard, they are positive integers. It says Alice and Bob play the following game. On Alice's turn, she must replace some integer n on the blackboard with n plus a. So a, change n, she adds a, and it will be n plus a. And on Bob's turn, it must replace some even integer n on the board with n over 2. So divide by 2, n over 2. N is even. Okay. Alice goes first. It is important who plays first. And then they alternate turns. If on his turn Bob has no valid moves, the game ends. It means what? It means all numbers are odd. Okay? Then Bob cannot play. After analyzing the integers on the board, Bob realizes that regardless of what moves Alice makes, he will be able to force the game to end eventually. Okay, means Bob can do something to reach a situation that all numbers are odd. Show that, in fact, for this value of a and these non-integers on the board, the game is guaranteed to end regardless of Alice's and Bob's move. It means what? If Bob can reach a situation that all numbers are odd and it's the turn of Bob and Bob should play. Means the game has finished. Then it says we should write this. The game is guaranteed to end of Alice's or Bob's regardless. Alice's and Bob's move. It means that eventually, regardless of Alice's and Bob moves, all numbers will be odd. And it's not important that Bob did what, Alice did what. Okay, for this problem, because we want to understand, this problem is a little hard to understand. The most useful idea that we want to use here, we want to consider a small example. Now, a small example on what? We can use a small example on A, on the numbers. I use a small example on M, the numbers that are on blackboard. Suppose M is 1. So we have one number on blackboard, X. Then in next step, the problem says Alice goes first. So it goes to plus A. X plus A. Then Bob divides by 2. It will be X plus A over 2. I want to first analyze the case that, for example, it doesn't stop. It goes up to infinitely many steps. Let's analyze that case first. Then it will be plus A, it will be X plus A over 2 plus A. Or we can write it as X plus X over 2. And look here, Alice plays, here Bob plays, here Alice plays. X over 2 plus A over 2. In next step, Bob divides by 2. So it will be X over 4 plus A over 2 plus A over 4. And then in next step, Alice adds a. It will be x over 4 plus a over 2 plus a over 4. Again, Bob plays. Okay, so and so on. Now let's add one more. For example, Bob plays x over 8 plus a over 2 plus a over 4 plus a over 8. And then Alice adds a. It will be x over 8 plus a over 2 plus a over 4 plus a over 8. Now, and so on. If, for example, we want to consider the case that it can go up to infinitely many steps. It means what? When it is Bob's turn, the number should be even. And let's consider those steps. Here, x plus a. Bob wants play here. X squared plus a over 2 here. X over 4. Here, this one. And here, Bob wants play. Now, in this step, as you can see, these numbers should be even because Bob wants to divide by 2. So in general, we see, okay, let's check. X plus a should be even. In next step, x over 2 plus a over 2. X over 2 plus a over 2. It will be x over 2 plus 3a over 2. It means that x plus 3a over 2. It should be multiple of 2. Next step, x over 4 plus a over 2 plus a over 4 here. It should be even, and if you factor from 4a plus a, 2a, 6a, 7a, x plus 7a, it is even. This number is even. This number is even. And then this one. X over 8 plus a over 2 plus a over 4 plus a over 8. Then we consider common denominator 8. It will be x plus 8a plus a 4a 12a plus 2a 14a plus 1a 15a over 8. And now let's consider in general. This number also should be even. So we can say x over 2 to the k plus a over 2 plus a over 4 up to a over 2 to the k. Okay, if we consider this, we factor from 2 to the k, we use common denominator and it will be x plus a times 2 to the k plus 2 to the k minus 1 plus 2 to the k minus 2 up to 1. And for calculating this, it is famous identity. You should memorize it in this formula. 1 plus r squared to r to the n equal to r to the n plus 1 minus 1 over r minus 1. There are around 5 important and basic identities you should memorize. One of them is this. So if you apply it here, this one, r is 2 for this identity and n is k up to k. So it will be x plus a times 2 to the k plus 1 minus 1 over 2 minus 1. All over 2 to the k. This number should be even, like previous times. Look, we don't write these things on our answer sheet. We are analyzing, and these things are for ourselves. We want to find the idea and then generalize it for the. We want to find the idea and generalize it for general m. M was the numbers on the blackboard. So x plus a times 2k plus 1 minus 1 over 2 to the k. This number is even. When it is even means it is, for example, 2t. So if you multiply both sides by 2 to the k, then x plus a times 2 to the k plus 1 and expand here minus a should be 2 to the k plus 1 times t. And then x minus a is equal to 2 to the k plus 1 times t minus a. This part is multiple of 2 to the k plus 1, so we conclude what? We conclude x and a, x minus a, is multiple of 2 to the k plus 1. A is what? A is the number that we add each step. Alice writes that number plus A. X is what? Is the first number. They are constant. So when a constant, and for any k, for all k, it can goes to infinity. So okay, it can go to infinity, and what's that? We have only one number, one integer that is multiple of all large number. It's what? 0. Only 0. So x minus a should be 0. So the only case that it goes up to infinity, it doesn't stop, it won't stop, is x equal to a. And let's analyze it. So the first number is a. Alice adds a, it will be 2a. Then Bob divides by 2, it will be a, and so on. Alice adds a, 2a, Bob divides by 2a. And we have a cycle. Okay, so we've understood that for n1, what happens? So let's prove the problem for n1. If it stops, because we have only one number, if they have to do the thing, for example, in first step, Alice have to select this one because we have only one number, and the problem is correct. If it ends, it doesn't really. It is not related that they play, for example, like they play what regardless of their playing. It will be stopped. Okay, so for n1 we've considered m1. Now consider we have two numbers or more. If you have more numbers, for example m2, you have some numbers like x1, x2. Okay, so let's analyze first m2, and then in m2 we can find completely the idea of the problem. Here, suppose that, for example, Bobs can do something that for example, we reach a situation that for example, the game will be stopped. In that case, we can say what? They can reach a situation that it is odd, and it is Bob's turn. Okay, and he cannot play. So it means Alice reached these two things. And the problem says Bobs can do something to reach this situation. But if we consider, because Alice always adds a to one of the numbers, if a is odd, it cannot happen. Why? Because in this step, for example, suppose we had x1 prime, x2 prime. Let's consider the cases. x1 prime, x2 prime. If it was odd, or odd, even, or even odd is same as odd, even, even. In this step, Alice can add a to one of them, then we reach e or not o. In this step, Alice can add odd to this one, it will be odd. And in this case, Alice adds a to one of them, it will be odd even. So Alice can do something to not reach o. So if a is odd, it's very rich contradiction because it says Bob can do something. Bob can do something to reach a state that all the numbers are odd. So lemma 1. Look, when we reach any good thing, we write it as a lemma. For example, maybe we reach 8 lemmas. Okay? We don't know which of them useful at the end. You should write all of them. For example, you write 10 lemmas. At the end, you will say, okay, 5 of them, 7 of them are useful, 3 of them are useless. Okay? Because now we don't know which of them are useful. We write anything that maybe can be useful. So a is even. The first thing that we can consider. Now let's analyze the case. If one number is a here, like we want to use m1. Okay, in m1 we said if they are equal, then it won't stop. So suppose if one of the numbers are a, Alice can add a here, it will be 2a. And then if Bob doesn't divide this by 2, Alice can play with other number. For example, it is the thing here, I said a is even, it's also useful for any m, not only m2, because we are working on m2. So here, look, if one of the numbers are a, Alice adds a. If Bob doesn't divide it by 2, for example, divide something else by 2, for example, second number, then Alice works here until Bob has to eventually work on this 2a, because Bob wants to reach a state that all numbers be odd. So when Bob divides this one by 2, it will be a, and then Alice adds again by a, 2a. So Again, if Bob, for example, doesn't divide this by 2, work on other number, Alice also work on other numbers, adds plus a, and then if Bob divide this again by 2, Alice adds a. Okay, so here we conclude, because Bob, from assumption of the problem, Bob can reach a state that all numbers be odd, but by this state, he cannot. Why? Because Bob can reach a state that all numbers are odd, and it is Bob's turn. But as you can see, Alice adds a, and it will be 2a, and now it's Bob's turn. So lemma 2, xi are not a. Okay, our numbers are x1 to xm, so none of them should be a. We've reached this one by using m1. We've considered that. Now, if you consider this one, as you can see, for example, it was a plus a, 2a, and something like this. We can say, suppose, for example, we have, instead of a, 2a. Okay, if we want to say also 2a is bad. Why? Because if you have 2a, Alice doesn't do anything with this, adds other number plus a plus a. Now, eventually Bob should change this, because Bob wants to reach a case, all numbers should be odd, and it is Bob's turn. So Bob divided by 2a, and again, like previous one, Alice adds a to a. Again, if Bob doesn't divide by 2, Alice works on other numbers until Bob divided by 2 again, and then Alice adds a. Okay, so 2a is also bad, and we can generalize it. 2 to the k times a also, it seems to be bad. Why? Because Alice doesn't do anything to this number, then Bob has to divide it by 2, and then it will be 2 to the k minus 1a. Again, Alice doesn't do anything with this. Bob should divide by 2 until the case that Bob divides by 2 and reach a. In this case, Alice adds a. It will be similar to previous proof. So, lemma 3. xi shouldn't be 2 to the k times a. Now, because we have 2 to the k, we guess that maybe we should work on v2 of these numbers. V2 of a number is what? V2 of, for example, a number S is maximum power of 2 that divides S. Means what? For example, V2 of 12 is what? Is 2 V2 of 12 is 2 squared times 3. And look, this part, it's 2. Maximum power of 2 is 2 to the 2 that divides 12. 2 to the 3, 8 doesn't divide this. For example, V2 of 30 is V2 of, it is 2 times 3 times 5. The maximum power of 2 that divides this is 1, because 2 to the 1 divides 30, but 2 squared doesn't divide this. Okay. Now, let's consider, for example, the case that we want to work on x1. We said x1 shouldn't, on one number, for example, xi, any number, for example, without loss of generality, let's work on x1. We said x1 is not 2 to the k times a. So, suppose v2 of x1, and we know a is even, by lemma 1, a is even. Suppose v2 of x1, because let me tell you something. When we have, for example, x1, then if Alice plays x1 plus a. If v2 of x1 is less than v2 of a, for example, means what? For example, x1 is 2, but a is 8. So 10. Look, v2 of 2 is 1. It has only the power of 2 is 1. Again, here is 1. Again, for example, if for example, we add 8 to this one, it will be 18, and the power is what? The power of 2 is 1. So, let's consider something. If v2 of x1 is less than v2 of a, let's see what happens. In this step, I want to say that if we work on x1, power of x1 cannot be increased. Why? Because at first, if it is Bob's turn, we have some numbers also. For example, maybe Alice plays with other numbers. If Bob divides by 2, then here we have x1 over 2. If it is not odd, I want to say that Bob can do something that reach to an odd number by starting from x1. Why? If x1 is odd, then it will be okay. I want to say that only for x1. If we want to only focus on x1, Bob can reach an odd number here, and then in next step also it will be odd if we do anything to this. We want to prove this. If we reach an odd number, then Bob cannot do anything, and if Alice do anything, she adds by a, and because a is even, odd plus even is odd. So I want to prove that in this case Bob can reach an odd number, and then after that we proved here all of them should be odd. If x1 is odd, the problem will be solved. If x1 is not odd, if it is Bob's turn, Bob divides by 2. If it is not Bob's turn, Alice adds by a. So in this case, what happens? We have x1 plus a. I want to prove v2 of x1 plus a equal to v2 of x1. Means the v2 won't be increased. And in this case, v2 of x1 over 2 obviously is v2 of x1 minus 1. So if Bob plays, then Bob decrease v2 of x1, v2 of the number by 1. If Alice plays, v2 won't change. So here we can conclude each term, each step that Bob plays, Bob decrease by 1, and Alice cannot increase this v2 of that until Bob divides by 2 to reach an odd number. And after that, this number is useless. Bob can work on the other numbers. Let's prove this one. Because v2 of x1 is less than v2 of a, we can say x1 is 2 to the, for example, t times r1, t1 r1, that r1 is odd, okay? It means we consider this t1. And now consider this t2. So a is 2t2 times r2, which r2 is odd. And we know t2 is greater than t1, okay, from here. So x1 plus a equal to 2t1 r1 plus 2t2 r2. And if we factor, because t1 is less than t2, if we factor from 2t1, it will be r1 plus 2t2 minus t1 r2. Because t2 is greater than t1, this part is even. Because it is odd, this part is odd. Odd times 2 to the t1. This number, v2 of this number, will be t1. So v2 of x1 plus a is t1. And v2 of x1 was what? t1. Okay, so we've proved that if v2 of x1 is less than v2 of a, Bob can do something to reach an odd number, and for this number, Bob can do something to stop this case. Okay, so let's call this lemma 4. Lemma 4, if v2 of xi is less than v2 of a, Bob can change this number to an odd number eventually, and after that step, the number is always odd. We proved this. Okay, now consider the case that v2 of xi, for example, equal to v2 of a. We want to see what happens. In this case, xi. If it is Bob's turn, Bob divides by 2 if it is Bob's turn. Bob divides by 2, and we reach xi over 2. And we know it is at least 1 because a is even from lemma 1. So we know because a is all even, xi is also even. If we divide by 2, if Bob's divide by 2, then it will be this, and v2 of xi over 2 is v2 of xi minus 1, and it is less than v2 of xi, which is v2 of a. And because v2 of this number that we've reached is less than v2 of a, it will be like lemma 4. By lemma 4, Bob can reach an odd number. By lemma 4, Bob can reach two odd numbers. But if it is Alice's turn, then we can say what? xi, Alice adds a. It will be xi plus a. Now I want to consider v2 of xi plus a is what? Suppose here, let's consider this, it is t3. So, xi is what? Is 2t3 r3. A is what? 2t3 r4, because power of two of them are equal. Now, xi plus a will be what? You can factor, it will be 2t3 r3 plus 2t3 r4. So it will be, if you factor from 2t3, it will be r3 plus r4. Odd plus odd is what? Is even. Okay? So we conclude that v2 of xi plus a is greater than v2 of xi. And because v2 of xi is v2 of a, we've reached the case that the power of this part is greater than power of a. So we should analyze the case that power of the number that we have is greater than power of a. So let's consider this case first. If v2 of xi is greater than v2 of a, in this case, we say, okay, if we have xi, if Alice plays and adds by a, then if you factor from this, for example, x, it will be xi plus a. When the powers are not equal, like this, the sum will be v2 of that will be equal to a smaller one. And easily we can prove by the form that I've showed you here. By this form, 2t3r3. And so let me tell you the reason is what. For example, suppose this one is w1, w2. So v2 xi is 2 to the power of, for example, w1 times r. For example, without loss of generality, consider r1 because it's not related to previous one. And a, for example, is 2w2, r2, r1, r2 are odd, so xi plus a is what? 2 to the w1 is 2 to the w2 is a smaller one, so we can write 2 to the w2 r2 plus 2w1 minus w2 r1. This part is even, this part is odd, so sum of them is odd, so we conclude v2 of xi plus I is w2 as I said here. Now here we've reached this step again. So let's see what can we say. I want to prove that if v2 of xi is greater than equal v2 of a, Alice can do something to, for example, Alice can do something that always that number be even. Why? Let's see. Suppose at first the number we start with this part. v2 of xi is greater than this. Alice adds a. Now we know v2 of xi plus a equal to v2 of. If we have this, I think if she does here, then Bob can divide by 2 and then it will be bad because v2 of that will be less than v2 of a. So let's do something. Alice doesn't do anything. Suppose v2 of xi is greater than v2 of a. Alice only adds to other number, for example by a. Eventually, because Bob wants to reach a state that all numbers be odd, so Bob should divide this one by 2, xi by 2. Alice waits up to the case that we reach to the state that v2 of this number equal to v2 of a. Okay, means xi divided by 2. Here we have 2 to the w1, w1 minus w2, because 2 to the w1 minus this is 2 to the w2. So Bob divides by 2 up to this part. Now, in this case, V2 of this number, xi, over 2 to the w minus w2 equal to V2 of a. In this state, Alice adds by a. We've analyzed this here. Then this number V2 of xi plus I will be greater than V2 of a. Alice adds by a 2 to the w minus 1 plus a. Now V2 of this number again will be greater than a. Okay, it will be similar to V2 of xi. Again, Alice doesn't do anything, adds other things by a up to the case. For example, Bob divides by 2 to reach the case that again we reach a number, for example L, that V2 of L again equal to V2 of A. In this state, Alice adds again by A. And then L plus A, V2 of L plus A will be greater than V2 of A. And again, Alice doesn't do anything, works on other numbers, and then Bob should divide by 2 up to this. And with this way, Alice can do something that Bob cannot reach, an odd number by starting from xi. Okay? So we've proved that lemma 5. Because the problem says Bob can reach a state that all numbers be odd. With lemma 5, we should say for all I, V2 of xi are less than V2 of. And now, if this thing happens, we can say it satisfies assumption of the problem. Why? Because if we start from x1, by lemma 4, Bob can reach a state that this number be odd. Then this number is always odd. Bob doesn't do anything with this number, then it starts with x2. If x2 is not odd, Bob focus on this and reach it to odd numbers, and then up to xm reaches to odd number, then all numbers are odd. And for example, if it is Bob's turn, the game will be stopped. If it is Alice's turn, Alice is add by a. Again, it is odd because a is even from lemma 1. Now it's Bob's turn, and Bob cannot do anything. Okay, so we've reached this. Now we should prove what? We should prove. We know V2 of all numbers are less than V2 of a. We should prove that it is not important Alice do what and Alice does what and Bob does what. Always with, regardless of their playing, they reach all m odd numbers. Let's prove this part. If it is x1, we know V2 of x1 is less than V2 of a. Suppose it is x1, x2 to xm. I define a function f. Defining a function is so much useful in many problems. Also, BMO for UK, for USA, for IMO, I define this function V2 of x1 plus V2 of x2 to V2 of xm. When these are the numbers x1, xm, I mean the numbers on the blackboard, some of V2 of them. If Alice plays, it will be x1 plus a. V2 of this number won't change. But if Bob plays, it's not important. Divide this one by 2, this one by 2, this one by 2. He divides one of them by 2, one even number. And then it will be x2 by over 2, and V2 of x2 will be decreased by 1. So after Alice plays and then Bob plays, for example, suppose f is c. In this step, f will be c minus 1. Again, it is not important. Alice does what, Bob does what. Again, f will be c minus 2. And f cannot be negative, because if all of them be odd, f will be 0. And because f is at least 0, we know that there is a step that it will be stopped. We will reach f0, Alice plays, Bob plays. And after this step, Alice plays. Then Bob cannot play, because f is 0 means all numbers are odd and Bob cannot do anything. Okay, this problem was a good application of considering a small example. Let me write some homework for you. For example, I can write from IMO. We have also some problems you can do as homework. Also from BMO, which is British Mathematical Olympiad. Let me write. So solve this problem. You can solve it with a small example. It is for IMO 2020. And the next problem that you can do as homework is problem of BMO. It's for UK. I also released the solution of this for the first time. It is for British Mathematical Olympiad Round 2, 2023. Okay, last BMO Round 2. BMO and USAJMO are two most prestigious National Mathematical Olympiad. It's good to work on both of them. It helps you. Also, for other example, other national Olympiads, International Mathematical Olympiad, this is the most important idea. Consider a small example, analyze the problem step by step, and try to gather tiny things you've proved, and then prove the whole problem. And as you can see, I proved many lemmas. Xi equal is not a was not useful, but xi is not 2 to the ka also was not useful. This one was useful. Okay, but they helped us. Okay, as I said, at the end you will understand which of them useful, which of them are not useful. Okay, so analyzing the problem is so much important. Okay, if you want to learn important ideas, for example, considering a small example, how to approach a problem, important ideas and formulas you should memorize, you should learn them in geometry, combinatorics, number theory, and algebra. Feel free to send message to my WhatsApp number in the description comments. And try to solve these two homeworks. And please don't forget to subscribe, turn on the bell, and like the video. Thanks. Bye. Last problem of USAJMO. Question number 6, 2023. Isosceles triangle ABC with AB equal AC is inscribed in circle omega. Okay, let D be an arbitrary point. So it is ABC, AB equal AC. Inscribed in this circle omega. Let D be an arbitrary point inside BC such that, so D is something, for example, here. BD is not equal to DC. So let's move for drawing the graph. Let's draw the line AD here. Let's minimize it. Okay. AD is some point here. And this one, it says what? It says DB arbitrary point such that BD is not equal to DC and ray AD intersect omega again at E. Other than A, because it is A intersect this line intersecting A and E. Point F other than E is chosen on omega such that DFE is 90. Okay, so for example, DFE is 90. Let me tell you how to find, for example, F. Let me show you something here. So look, I want to see what points have 90 degree and see the DE in 90 degree. These points have what property? Look, if you consider a 90 degree here, for example, let me show with line. It is, for example, 90 degree. It is 90 degree. Because they see this DE with 90 degree, they are cyclic. And the reason is what? The reason is this. If we have, for example, this one, and as I said in also another geometry problem of this exam, A1 equal to B1 if and only if ABCD is cyclic. Okay, angle A1 equal to B1 if and only if it is cyclic. So it is 90-90, and for example, we can see also some other 90s here. In general, for any angle, it will be two circles because all of them on this side, CDE, with, for example, same angle, so they lie on a circle, and also on this side. But because in special case of 90, these two circles will be one circle. Okay. So if I want to show you like this, for example, the circles, if it is not 90 degree, it will be two similar circles. One of them this, the other one this, and all, for example, these angles, see this side with same angle, all these points, this, and also on the other side. But when it is 90, then the circle on each side will be, the diameter will be DE, because when it is 90, it sees diameter, and in both of them, so if we draw a circle with diameter DE, it covers all angle. Let's see, this is 90. So if we draw, for example, some circles like this, then we understand, okay, it is our F. So let's draw that circle. Okay, if we draw this circle, as you can see, we can say, for example, it is F. Okay, and DF is 90. Okay, it is not necessarily tangent to this one. Okay, let's see the rest says what? The rest of the problem. Line FE intersect ray AB and AC at point XY. So let's do something. Let's extend AB and AC. It will be some point like this. And this one we should extend only like this. Okay? So if we draw EF, it intersects like this, and this point like this one. Okay? So it intersects AB at X, AC at Y, respectively. Prove that XDE equal to EDY. XD, so we should connect X to D. So X DE and this. So look, knowing these properties helps you, for example, to draw this circle. And why this circle is good? Because if you consider the intersection, we set any line on this circle CDE with 90 degrees. So if we consider, for example, this one, if we consider this one, if we consider this one, all of them are 90 degrees. So for example, let's consider this one K, let's consider this one L. So it is 90 degree, it is 90 degree, it is also 90 degree. Now here, like previous problem of geometry that we solved today, let me show you. The previous problem of geometry was, let me tell you, this one. As you can see, here I told a property that if P is outside, let me copy this word. If P is outside, PA times PB equal PC times PD. And we can say, let me tell you exactly this idea with other way. I can say that, suppose, for example, P is here. It is ABCD. PA, for example, BCD. PA times PD equal to PB times PC. If and only if ABCD is cyclic. As I told you, we have 4 properties, main and basic properties. In cyclic quadrilaterals, one of them is this. And the 2 problems of USAJMO 2023 could be solved with using this. Here, try to see, we can see anything like this. And X is outside as a hint. If you see, let's consider it is omega 1. XE times XF. Or let's start from XKD to write it better. XK times XD equal to XE times XF by using omega 1, this circle, green circle. And if you apply omega, XE times XF, it's what times what? XB times XA. Okay? And because XK, XD equal XB, XA, we said it is equivalent, means if PAPD equal PBPC, ABCD is cyclic. So, because here we see that XK, XD equal XB, XA, what quadrilateral is cyclic? AB, KD is cyclic. If we use the same thing from Y, we can say Y L times YD because of omega 1. And we call it power of point Y with respect to this circle. Okay, the definition, the name is this. YL times YD equal what times what? YF times YA. And if we consider with respect to omega, YF times YE equal to YC times YA. And again, because of this one and this one, similarly, we can say which quadrilateral is cyclic? ACLD. Okay. Now, if we draw the lines, we want to prove. At first, let me tell you something. We know it is alpha, and we found that ABKD is cyclic. So, what is the other angle? Because the problem says ABCD is isosceles, ABC is isosceles triangle, so it is alpha. It is alpha. And if we draw this line, because ABKD is cyclic, so let me consider ABKD is cyclic here. So it is alpha, see this side, so it is also alpha, okay? So it is alpha. Similarly for this one, A, we said what? ACLD. ACLD here. If we consider again this alpha, if we draw this, similarly in this cyclic quadrilateral, let me draw like this. It is alpha, see this side, so it is also alpha, okay? So let me draw another alpha here. Let me minimize the pen. Okay, so it is alpha. Now the problem says what? Why this angle equal to this angle? The problem is, if this angle equal to this angle, because it is alpha, we conclude that these two things also should be equal. Let me, like, because we have many things, let's focus only on this part. Let me just show this part, we don't need. Okay. We want to prove what? We want to prove D1 equal to D2. If D1 equal to D2, because it is exterior angle of this, we conclude that, for example, A1 also should be equal to A2. So D1, let me make D1 equal to D2 is equivalent that angle A1 equal to angle A2. Okay, let's write the angle symbol here. So if A1 equal to A2, here this angle is 90 plus alpha, this angle 90 plus alpha, so it is equivalent in these two triangles. It is equivalent that E1 equal to E2. So we know all these things should be equal if the problem is correct. E1 equal to E2. And now we conclude what? AKE, then all three angles of AKE, then it is equivalent by two angles. That all angles in AKE should be similar to ALE. Okay. And because AE is common in both similar triangles, so we conclude that it is equivalent that AKE is congruent to ALE. So we are analyzing this problem. Let me also erase this part. Let's just erase these two lines and show this part. Okay. So let's also maximize this a little. Okay, what can we say here? For this part, I want to tell you something that we call it ratio lemma. The name is not so much famous, but it's so much important in problems, in many problems. Also in, for example, AMC, AME, not necessarily in, for example, high-level exams. It is what? It says if you have A1, A2, if it is P, sine, we can call it ratio lemma, but the proof is not hard. You should use two sine rule. Sine A1 over sine A2 equal to VP over PC times PC times B over C. Okay. Or you can say BP over PC times sine B over sine C. And if you prove one of them, the other is easy, because why? B over C, sine B over sine C by sine law, so we want to prove only one part. Let me tell you the proof. So we want to use two sine law. If you use sine law in triangle ABP, then we have what? Sine A1 over, let's write the angles, sine B, suppose it is P1, it is P2, equal to sine P1. So sine A1 sees what? A1 sees what side? BP. Sine B sees what side? AP. Sine P1 sees what side? AB or C. Now, if we use again another sine law, we can call it also double sine law in triangle APC. Like we have a important point, double Pythagorean theorem. It's also so much useful in AME and other exams. In APC, sine A2 equal to sine C equal to sine P2 in triangle APC. A2 sees PC, C sees AP, and P2 sees B. So if we divide these two terms, sine A1 over sine A2 times. Here, look, if we consider the division between them, sine A1 over sine A2 times PC comes in numerator. Because you say this times reciprocal of this will be PC over BP. Okay. Sine B, sine C, AP will be cancelled, so it will be sine B over sine C. And this part, P1 plus P2 is 180, because it's a straight angle. When two angles are 180, sine of them are equal, or some cosine of them are negative of each other. So because sine P1 equals sine P2, they will be cancelled, so it will be B over C. Now, here, you can say, okay, sine A1 over sine A2. If we take this to right hand side, it will be reciprocal of that. BP over PC. So it will be BP over PC times this one, sine B over sine C, which is this part, or BP over PC times B over C, which is related to this part. Okay? So we proved ratio lemma. Now I want to use it here. Here, alpha 90. So let me copy this part because we want to use to. If you don't know that, you can see it and use it. Let me copy. Let me copy again. Okay. And let's draw a rectangle around this. Okay. Now, if I use ratio lemma in KAE, and here AP, here KD, ratio lemma, then we can say sine alpha over sine 90 equal to AD over DE. Okay. AD over DE times, you can say KE over KA. Now, if you use in triangle, it is A here, in triangle ALE and line LD, If we apply ratio lemma again, sine alpha over sine 90 equal to a d over d again times LE over A. LE over LA. Okay? Now, if you compare these two things, left hand side equal to left hand side, so right hand side equal to right hand side. Also in right hand side, AD over D is common, so the second fractions are equal. So KE over KA equal to LE over LA. Let's copy this figure again and paste it in another place and consider this property. Okay, the property was, let's paste it here. The property was this one, KE over KA equal to LE over LA. So here, now, look, this angle equal this angle. Angle AKE equal to 90 plus alpha equal to angle ALE. And also, KE over KA by this property equal to LE over LA. So by these two properties, it's two sides and angle between. We conclude that it's one criteria to prove that two triangles are similar, for example, like two angles. Triangle AKE is similar to triangle ALE. And do you remember we said because AE is common in both of them, so the ratio is 1. So we've concluded that AKE is also congruent to ALE. Okay, we are analyzing. Now, so this angle is beta, this angle is beta. We don't need to consider congruency, but something I wanted to tell you. So it is beta, it is alpha. So D1 is what? It is exterior angle alpha plus beta. And D2 is what? Alpha plus beta. So we proved that D1 equal to D2. Okay. So for this problem, again, we've used on cyclic quadrilateral. Let me write a homework that is for IMO and you can solve it. You can do this problem as homework. And there are lots of problems in IMO related to cyclic quadrilaterals, but this problem doesn't need any new thing. So if you want to learn how to approach problems like this, cyclic quadrilaterals, for example, here, this part that, for example, this circle was useful. Okay, that, for example, they see 90, the angles that see the same side with equal angle, they lie on two circles. On each side, one circle. When it is 90, it will be one circle. These are ideas. We have also another ideas in geometry. Let me tell you some of them. Look, the ideas, for example, here, find middle angle. It is one idea. You can solve this IMO problem too. And also, let me tell you, this idea, you can use that to solve this problem, 2018. These are some other ideas, for example, this one, and Grimm's theorem, different views. It's another idea useful in many exams. Here you can use it. There are lots of ideas like these things. Okay, if you want that I cover these ideas for you, if you want that we work, these are only ideas. We work on the ideas after memorizing the important formulas that in geometry we have. If you want to learn those ideas, how to solve problems with those ideas, as I said before. Also in combinatorics, we have similar ideas. If you want to learn them, feel free to send message to my WhatsApp number in the description and comments. Please don't forget, I will release also other years of IMO. I release problems of hints for SUMAC, Stanford summer camps. Promise, if you want to learn how to approach, for example, problems like these, M.Sc aiming from basic level up to IMO, the approaches are so much important, how to start a problem. And if you want to learn them, feel free to send message to my WhatsApp number in the description and comments. And please don't forget to subscribe, turn on the bell, and like the video. Thanks.